Do you think it's possible to split a neutron from its own spin? It may sound like a hallucination from a sleep-deprived physics student, but it's exactly what some scientists now claim. They call it the Quantum Cheshire Cat, named after the trippy cat from Alice in the Wonderland, that disappears but leaves its grin behind. And if you are wondering, why are quantum physicists so obsessed with cats? Well, I don't know, but I don't mind it either. But seriously now, is this actually possible? Can a particle really be in a different place than its own spin? To figure that out, we have to look at the experiment itself. And well, to catch a runaway spin, you need a trap. And so the scientists decided to build one. And by the way, if you are wondering what the heck a spin is, just think of it like a tiny built-in magnet that can point in any direction. But back to the experiment. Imagine a road that forks into two. In a normal world, you can either take the top path or the bottom path. But if you are a quantum particle, you kind of have commitment issues. Instead of just choosing one, the neutron kind of takes both at the same time. And if you are wondering, but wait, is the particle really physically splitting? Well, that's a story for another video. Then, to actually set the trap, scientists merged the paths again and rigged the experiment so that only neutrons taking the top path could ever reach the detector. This was super easy to verify. If they blocked the top path, no neutrons arrived. But if they blocked the bottom path, well, every single little bastard still made it to the end. And here comes the magic trick. But before the physics police shows up, yes, I'm simplifying this a lot, just so you don't run off watch actual cat videos. So, to find out where the neutron spin is, scientists used a sneaky little magnetic device. First, they placed it in the top path, where all neutrons were supposed to be. But the device said, nothing to see here, brother. It didn't detect any magnetic signal, so the spin of the neutron couldn't be there. But when they scanned the bottom path, where no neutrons should be, suddenly the device claims the spin is right there. So here's the spicy conclusion. The particle traveled the top road, but its magnetic spin took the bottom one. Which raises a few minor questions, like how can a particle exist without this property? Or how are we measuring the spin without collapsing the quantum state? Back in 2012, this was all just a failed experiment. It should work according to the math of quantum physics. But nobody has actually seen it yet. So with zero experimental evidence, the reviewers of this paper were pretty skeptical. But the authors were not just some random grad students. The lead author was Yakir Aharonov, a certified quantum legend and a sort of a scientific rebel who specialized in impossible ideas. Decades earlier, he and his mentor David Bohm came up with a wild idea. What if a particle could feel a magnetic field, even when the strength of the field is exactly zero? Sounds like another quantum nonsense, but experiments eventually proved them right. And so they thought long and hard about how to name this revolutionary idea, and they decided to go with the Aharonov-Bohm effect. So Aharonov had a reputation, the guy who is right even when everybody else thinks he has completely lost his mind. 2 years after scientific bickering, the paper finally got the stamp of approval, and those who doubted him didn't have to wait long for the I told you so moment. In 2014, an experiment showed this really works, with neutrons. And then again in 2016, the experiment worked with photons and photons polarization. So the Quantum Cheshire Cat wasn't just a theory anymore, it was real. Or so we thought. Because soon after, the critics came back stronger than before. 3 different research groups dropped their papers, each one taking a swing at the innocent Cheshire Cat from a different angle. But to figure out who is actually right, we have to dig deeper into the experiment itself. The experiment used neutrons with a specific spin. Recall that the spin is sort of like a tiny built-in magnet that can point in any direction. For simplicity, we will call spin pointing right plus, and spin pointing left minus. Now imagine a neutron with a spin plus entering this setup. On the bottom path, they placed an extra device that flips the plus spin into minus spin. So after the paths merge, we have a mix. Some neutrons still with spin plus, others now with spin minus. But then, right after it, they added a spin filter that only lets through neutrons with plus spin. So any neutron that actually made it to the detector? It had to be plus spin, which means any neutron that makes it to the end must have taken the top path. Now comes the tricky part. How do you measure where the spin is? In the quantum world, that's a serious problem, because the moment you try to measure the spin directly, you mess up the experiment. If you measure the spin in one of the paths, well, the experiment is ruined. You force the neutron to show up, collapsing its quantum state. But fear not, because science bros have a solution, and it's called weak measurements. The idea is that you kinda sorta measure the spin anyway, but so gently it barely counts. So basically you only get a small hint of what the spin could be, but you don't collapse the quantum state. Then you do it again, and again, like million times, until you can kind of reconstruct what the spin was without fully measuring it. And by the way, can you guess who invented this clever magic trick? Once again, Yakir Aharonov. He came up with it in 1988, and since then it has been widely used in quantum labs everywhere. Okay, but back to the experiment. To figure out where the spin is, we use that weak measurement trick, by placing a very gentle magnet in the neutron's path. What does it do? Well, it slightly rotates the spin. So for example, a spin that started out as plus won't be a perfect plus anymore. It will be slightly tilted. Let's call this an almost plus spin. Okay, so now what happens when we drop this tiny magnet into the top path? Remember, every neutron that takes this road starts as a pure plus spin. The magnet gives it a slight twist, so now each one is carrying an almost plus spin. The next stop is the spin filter. What happens now when these almost plus spins neutrons arrive? Well, most of them will still make it through, but few of them will get filtered out. That slight rotation causes a small drop in the number of neutrons reaching the end. For example, if the magnet wasn't weak, but say it rotated the spin by exactly 90 degrees, you would get exactly half the neutrons through. That's just how the spin filtering works. And now, let's see what they actually measured. They sent in neutrons with pure plus spin, dropped a weak magnet into the top path, which would twist those spins just slightly into the almost plus spins. These neutrons then traveled to the spin filter, which would now block some of them, depending on how much the spin got rotated. So, did it happen? Well, no. Absolutely nothing changed. Every single neutron still passed the filter and reached the detector. It's like the weak magnet didn't have any effect on the neutrons. How is that possible? Well, the explanation is this. The neutron was on the top path, but its spin wasn't. Because if the spin was there, the magnet would have messed with it, and some neutrons would have been filtered out, but they were not. And that, my friend, is the quantum equivalent of a magic trick. The neutron went one way, but the spin the other way. And now again, quick message to the physics police. I tried my best to simplify this experiment, but I definitely skipped some technicalities that were just pain in the ass. But if you are the type that enjoys pain, feel free to dig into the actual papers, they are linked down below. So, was the experiment success? It sure looks like it. It's exactly the kind of bizarre result Aharonov had imagined. But there is a catch. Does this really prove that the spin of a single neutron can be separated from the neutron itself? Because remember, the conclusion comes from weak measurements. The measurements that you have to repeat like million times. So the critics were quick to point out. You didn't actually measure a single neutron. You measured millions and then averaged the result. Even now, 10 years after, they are still arguing about this. So here's the takeaway. Apparently, quantum physics will forever be the heavyweight champion of scientific arguments. It's kind of hilarious how one of the most accurate physics theories is also the messiest one, full of interpretations, contradictions and disagreement on what's actually real. If your brain hasn't melted yet, I talk about that entire mess in here. So hey, thanks for watching, and please don't leave your subscription behind, you are not a quantum particle. See you next time.